In this question, we're going to continue with the same population of high school students, but the question we ask is going to be a little bit different. So using that same population of SAT scores with a mean of 500 and a standard deviation of 100, Part A asks, what score would I need to qualify for acceptance into an engineering school if they only accepted SAT math scores in the top 10% of the class? So thinking about our SAT scores, we have a normal distribution, and the top 10% of scores would be on the right side of my distribution, or the larger X values, or the bigger SAT scores. So the question we're asking is, what is that SAT score that's the cutoff to be in the top 10%? If I consider the entire curve having an area of 1, and think about just the top 10% of the curve, the top 10% of SAT scores, we're talking about an area of 0.1. So the question goes to, what SAT score do I need to have an area to the right of that X value to be 0.1? So I'm going to answer this question using the standard normal curve. And I'm asking the same question over here on the standard normal curve, but I'm changing it into what Z value is it that has an area to the right of 0.1. Now to find the Z value, I'm going to use the normal table, but I'm going to use it backwards how I used it before. What I'm going to do with the table this time is I'm going to look up an area and then see what Z value applies to that area. I have to remember that the normal table only lists areas to the left of particular Z values. So if I'm searching for a Z value that has an area of 0.1 to the right of it, what I'm actually going to look up is an area of 0.9. That would be this big blank space over here. A Z value that has an area of 0.9 to the left of it would be the same Z value that has an area of 0.1 to the right. Going over to my normal table, I'm not going to look up a Z value this time, but I'm going to look up the area that's relevant to me. So I'm searching for an area of 0.9. Now I know this Z value is going to be on the right side of my distribution, so it's going to be a positive Z value. So when I go to my table, I'm going to go to the positive Z page. And this time I'm searching through these 4 decimal numbers, which are all areas. And I'm searching for the area 0.9. Or if I want to use 4 digits, I'm searching for 0.9000. I may not find that number exactly, but I'm going to do the best I can do with the table that's given to me. So I can see here that the areas are increasing as I read left to right and as I go down the page. And that's because the Z values are increasing, getting further and further to the right, making the area to the left larger and larger as well. As I'm searching through the rows, and I get closer and closer to 0.9, what I'll notice is that the closest value to 0.9 that I can see is this value right here, 0.8997. If I use the table backwards, what I can do is figure out that a Z value that has an area of 0.8997 to the left of it is the Z value 1.28. An area to the left of 0.8997 is a Z value of 1.28. Taking that information back to my problem. In the last problem, I used a formula to convert SAT scores, X values, into Z values. Rearranging this formula, I can use it to solve for X in terms of Z. So I'm going to use this formula right here with a Z value of 1.28. Essentially, I have to be 1.28 standard deviations above the mean to be in the top 10% of a normal distribution? Well, as far as SAT scores are concerned, 1.28 standard deviations, since the standard deviation is 100, I multiply that together and add it to the mean of 500, which gives me an SAT score of 628. A z-value of 1.28 has about 10% of the area to the right of it, and in our population, an SAT score of 628 has about 10% of the values to the right of that. I can do a similar method for finding the top 20% in part B. It's the same theory. I want to find a z-value that has 20% of the values larger than it, or an area of 0.2 to the right. So to find this z-value on the table, I'm actually going to look up the area to the left, this blank space, and that's going to be 0.8 because I subtracted 0.2 from 1. Going back to my table, I'm going to try to find an area of 0.8 or 0.8000. Scanning through my table, I see that the closest value I can find is 0.7995. That's the area to the left of z equals 0.84. To be in the top 20% of any normal distribution, you have to be 0.84 standard deviations above the mean. So the question is what SAT score is 0.84 standard deviations above the mean? Well, 0.84 standard deviations would be 0.84 times 100, or 84 points. So adding that to the mean of 500, that gives me an SAT score of 584.